We have some nice, thanks, Elias, nice papers. The first one is going to be presented by Michael. Michael, please take it away.
Okay, hold on, let me share the screen. Hold on a second. Okay, hold on. I had it open. There we go. Okay, so you can see this?
Yes. Yep.
All right, so I'm presenting a pitch on the paper I co-authored with Dr. Betty Chin titled Know What You Know, Predicting Behavior for Learning-Enabled Systems When Facing Uncertainty. So our research has largely been focused on managing uncertainty for learning-enabled systems. And for this work, we've demonstrated this on an object detector for an autonomous vehicle. And one of the challenges with these data-driven learning-enabled systems is just how to manage real-world uncertainty, because the real world's full of corner cases that can fall outside the training distribution for your learning-enabled system. So this is particularly challenging for safety critical applications, because for these applications, you need fail-safe coverage for all potential hazards, even the untrained conditions, because otherwise the result can be injury to humans or even death. So we've asked ourselves, how can we determine when an LES has encountered phenomena outside of its comfort zone? And so we've, on our object detector that we've trained, basically this object detector can locate objects or relevant objects in the scene, such as vehicles or pedestrians, by these bounding boxes and categorize the type of object. And we trained an object detector to get 88% recall, but that's training data that mostly contains clear weather. So what we're concerned with are these known unknown phenomena, such as a raindrop falling on the camera lens, as shown in this example. So we can describe these phenomena, but we don't know how our object detector will respond to them. And what we proposed is the use of these behavior oracles that can both perceive the known unknown phenomena and predict how the neural network or the object detector will respond to this known unknown phenomena. And so what we've introduced is this framework called NWIL that can automatically assess these LESs under simulated phenomena and then create a predictive behavior model for the LES. So for example, if we give it the behavior oracle a rainy image like this, it will output both a perceived context to describe the rainfall, such as the angle, density, and intensity, but also the expected behavior category for the LES. So like in this example, it would predict that the object detector would fail to detect objects or the van in this image. So the way that we've set up NWIL, it basically works in two stages, where the first stage uses evolutionary computation to assess the LES under simulated phenomena. And this generates a set of behavior archives corresponding to all your behavior categories of interest, where, for example, in this image, each point corresponds to a different raindrop generated by NWIL, and the colors indicate the different behavior categories, where green is where we predict the object detector won't be impacted, yellow is where we predict it will be degraded, and red is where we're predicted to be severely compromised. So using this information, what we want to do is take given any image of a raindrop or some other known unknown phenomena, we want to be able to map it to somewhere in this behavior space defined by these behavior archives. So that's why in the next stage, we do this model inference where we create a separate neural network to act as our behavior oracle. And this neural network, again, will output a perceived context and an inferred behavior category. And the way this works is it takes the same input as our object detector, and then it produces it performs inference isolation, where it basically isolates the interference that we're interested in. And then it produces that into a feature vector that we then translate into the same characteristics we use to simulate the phenomena. So like in this example with the raindrop, that's going to be the position, the radius, and the blur. But that would change depending on the phenomena of interest that you simulate. And then the final step would be to classify the behavior into one of the behavior categories. So like in this example, it would predict that this raindrop is a behavior category 2, which corresponds to a severely compromised object detector. So in this case, when given this image, the behavior oracle both perceives the position, radius, and blur of that raindrop, and it predicts that the object detector will fail to detect objects in this situation. So I have a quick demonstration here to show how this would work in real time. Basically, given our object detector, it's able to detect the vehicles parked on the street perfectly fine without any interference. But as we start simulating a raindrop, you can see how the raindrop will obviously impact object detection. So this is without the behavior oracle intact. So we would just have no way to assess this if we were just using the object detector off the shelf. But when we use our behavior oracle at the same time, we're able to predict when the raindrop will start degrading and then compromising object detection. And on top of predicting the behavior category of our object detector, since we're also predicting the perceiving the context, we can use this to both locate and describe the interference itself. So this would help us identify not only is there a raindrop that would cause our detector to fail, but where that raindrop is. So in summary, software engineering is a challenging problem for learning-enabled systems, and we need some way to self-assess learned behavior at runtime. So we've introduced NWIL as a framework that uses evolutionary computation and machine learning to produce these behavior oracles that can both perceive context for known unknowns at runtime and infer the behavior category or behavior of your LES for self-assessment. So in future work, we'd like to fully integrate this into a MAPE-K-loop type self-adaptive framework to help adapt a learning-enabled system to known unknowns at runtime. So if you'd like more information, obviously this was a short summary, please refer to our full presentation and paper, and feel free to ask questions. That's all I have to say for now, so thank you for listening.
Thanks, Mike. For some time. So the next paper is going to be presented, I believe, by Anna. Anna, do you want to go ahead? We can see the presentation. Do you want to start?
We cannot hear you, Anna. Not yet.
Can you hear me now?
Yes.
Okay, I'm sorry for that. So previously when I asked the question, it was audible. Okay, so hi everyone, my name is Anna, and today I'm presenting our CEPTED paper titled Runtime Reasoning for Uncertain Observations with Subjective Logic in Multi-Agent Self-Adaptive Cyber-Physical Systems. As modern society increasingly relies on cyber-physical systems, these systems must act reliably when faced with different runtime uncertainties. The runtime uncertainties can be internal, originating from the systems themselves, or external, originating from the uncertain and changing environments or execution contexts in which the systems operate. Additionally, due to the limited range of the sensors, cyber-physical systems can only observe their context partially, which introduces another dimension of uncertainty in the system. A common approach to deal with uncertain and changing conditions at runtime while preserving the system's performance or certain quality objectives is to make the cyber-physical system self-adaptive. As all of us know, in architecture-based self-adaptation, a self-adaptive system, including self-adaptive cyber-physical system, is comprised of a managed element and an adaptation logic. And the adaptation logic is traditionally implemented according to the MAPE-K closed feedback loop. The knowledge in the adaptation logic, besides the adaptation goals, should keep models of both the context in which the cyber-physical systems are operating, as well as the cyber-physical systems themselves. However, due to the dynamicity, the changes and the uncertainties of the execution context in the cyber-physical systems, the models in the knowledge should be models at runtime, which are continuously updated during the system's operation to reflect the dynamic changes in both the context and the systems themselves. To update the model and accordingly the knowledge component in the adaptation logic, the need emerges for runtime information aggregation and reasoning of what each cyber-physical system individually observes. The problem that we solve in this paper is the following. Multi-agent self-adaptive cyber-physical systems are exposed to a variety of runtime uncertainties, resulting in inaccurate and partial observations, which potentially can lead to conflicting observations made by different cyber-physical systems. Unresolved conflicts can result in suboptimal decisions in the other phases of MAPE-K, and this can impact the overall performance of the adaptive system. As a result, there is a need for effectively aggregating the different observations before updating the knowledge, and this can also be seen as uncertainty resolution strategy applied at runtime. Although knowledge representation and runtime aggregation and reasoning are essential for building multi-agent self-adaptive cyber-physical systems, there's a scarcity of approaches for modeling the knowledge that allows capturing uncertain and conflicting observations from multiple decentralized cyber-physical systems based on which the knowledge is updated. As a solution in this paper, we present a methodological approach for knowledge aggregation that is domain independent and can deal with reasoning on uncertain, partial, and conflicting observations. Concretely, our approach uses subjective logic to update the knowledge in the adaptation logic at runtime by aggregating observations of the context made by each cyber-physical system in independence. Last year at SAM, as part of an accepted short paper, we presented the preliminary idea of aggregating knowledge with subjective logic, and this year we present the fully developed approach for the reasoning. Together with an improved implementation of an in-house built ROS-based multi-robot system, which served us as a testbed, we conducted extensive controlled experiments and evaluated the effectiveness and the sensitivity of our proposed approach. So in this work, we focus on multi-agent self-adaptive cyber-physical systems in which the MAPK loops are structured according to the master-slave pattern, meaning we have many decentralized monitoring and execution phases that are controlled by a single centralized instance of analysis, planning, and knowledge. And the analysis phase reasons on the uncertain, partial, and potentially conflicting observations from the decentralized monitors. And once the observations from the monitors are aggregated, they become knowledge. So very briefly, you can see here the architecture of our approach. So in each managed element, we have a monitor component. The monitor observes the context in which the cyber-physical system operates, and additionally does a minimal monitoring of the system itself. Based on these observations, the subjective opinion creator contained within the monitor creates binomial subjective opinions according to the formulas that are shown on the slide. And these binomial subjective opinions are then independently forwarded to the centralized analyzer. The analyzer contains the knowledge aggregator, which contains and fuses all the subjective opinions that are issued by the subjective opinion creators in the decentralized agents. The aggregated opinions are used to update the runtime context model in the knowledge. As part of our work, we identified 3 research questions which guided our evaluation. The first one is, how do different subjective logic aggregation schema influence the knowledge aggregation in these systems? The second is, can subjective logic-based knowledge aggregation in multi-agent self-adaptive cyber-physical systems correct faulty measurements? And the final question is, how does the value of the threshold impact the subjective logic-based knowledge aggregation in multi-agent self-adaptive cyber-physical systems? Finally, this is my final slide. Our results or our experiments reveal that long-term knowledge aggregation is not feasible by using the original subjective logic operators in isolation, and this limitation is addressed by a newly proposed aggregation schema, which is another contribution in this work. Proposed subjective logic-based knowledge aggregation approach is capable of correcting the observations of a faulty agent, and there is a trade-off between the number of tests that are completed and the accuracy of the agent, and the threshold can be used to tune the accuracy of knowledge aggregation to the desired level. I'm aware I didn't show any results just because of the time limitation, but I'm open for questions during the discussion. So thank you very much for your attention. Also, Ilias, who is the co-author of this paper, is in the audience, so both of us are very much looking forward to your questions. Thank you.
Thanks, Anna. Nice work. Next paper on reliability prediction, I believe is going to be presented by Max. Max?
Yeah.
Yeah, I see the slide.
Can you see my screen?
Yes.
Perfect. Okay. Yeah. So then, thank you. And hi, everyone. My name is Max. I'm a PhD student at the Research Center for Information Technology in Karlsruhe, Germany. And yeah, in the next 5 minutes, I want to give you a brief overview about our paper, Reliability Prediction of Self-Adaptive Systems Managing Uncertain AI Black Box Components. And yeah, the second author who contributed to the paper is Ralf Reusner from the Karlsruhe Institute of Technology. So in recent years, there have been a tremendous progress in artificial intelligence, and especially in the field of deep learning. So there are actually various use cases where AI has been successfully applied, such as we've seen before in autonomous driving, but also in human-robot interaction, just to name a few. However, the problem with AI is that the used models, and I'm referring here to deep neural networks, are very complex, so that we are not able to determine whether a prediction is correct or incorrect. And due to the lack of transparency and comprehensibility, we have to treat such AI components or models as black boxes. And this is of course pretty this uncertainty is of course very concerning in safety critical domains such as autonomous driving. Therefore, we advocate the use of MAPK-based self-adaptive systems to safeguard or manage AI components by monitoring certain properties and triggering reconfigurations when the AI component is likely to produce an incorrect prediction. Secondly, when using self-adaptive systems to maintain reliability attributes or properties, a couple of design decisions must be taken into account that are preferably evaluated before implementing the system. Therefore, we present a model-based approach that enables reliability prediction of self-adaptive systems, managing such uncertain AI black box components at design time. The approach is based on concepts from the domain of model-based quality analysis that have proven successful in predicting quality attributes for software architectures represented by models. So basically, our approach is divided into two parts. The first part of our approach relates to the question of how to use self-adaptive system to safeguard such AI black box components. And the problem that arises at this point is that a self-adaptive system is actually not able to fully observe the true state of an AI black box component due to the lack of transparency and comprehensibility. However, it must decide based on the state whether a reconfiguration is required or not. Therefore, we propose an approach that augments the monitor phase of a self-adaptive system with additional properties that allow to reason about the state of an AI black box component. We refer to this as decoupling the observation process because we can ignore the observations, which relate in our case to input data or the input space of the AI component, and focus entirely on the observed properties. Depending on the context, such properties might be variations of the sensor noise levels, but also more sophisticated properties such as robustness properties. The second part proposes an approach for design time validation of self-adaptive systems that are supposed to manage such AI black box components. In a nutshell, we extended an existing reliability prediction approach for static software systems. In addition, we apply a sensitivity analysis to the AI model with respect to the identified properties that augment the monitor phase, so that are the properties that I mentioned before. And the result of the sensitivity analysis is a conditional probability distribution or the sensitivity model determining the probability of observing false predictions for different property values and also with respect to the sensitivity model. The distribution is finally integrated in the existing prediction tool that we extended in order to observe how the overall reliability of the system varies for different property values. And finally, the approach is integrated in a model-based framework for evaluating self-adaptive systems from previous work. And basically the framework allows the evaluation of the decisions made by self-adaptive systems based on our reliability prediction approach. Okay, I see that the time is a little bit running out here, but let me just quickly say that we also demonstrated the applicability of our approach by a proof of concept. And if you're interested, then please have a look at the paper. And thank you very much for listening. And I'm looking forward to your questions.
Thanks, Mike. Very interesting work. So the next paper and the last one is on fairness. I believe Ali is going to present it.
Yeah, can you see my slides?
Yes.
Okay, perfect. So, hi, my name is Ali Farahani. I'm a researcher at Lero. I will present on behalf of my colleague at Lero and OU our paper named on adaptive fairness in software systems. We all are aware of problems of clear or even hidden unfairness in outcome of the software systems, like the unfairness of discrimination against different minorities by recruitment algorithm or a patrolling management system. These kinds of discrimination are mostly attributed either to the bias in the data or flaws in the algorithm but we think that primarily this problem is about the lack of explicit fairness requirements. However, it will raise another problem, how to capture these requirements completely at development time, which we think is almost impossible. Let's skip the latter one for a moment. Even with having all the requirements at hand, the solution in the literature for removing such discrimination from the system is either to fix the bias and retrain the system, or to re-implement the algorithm or the system. We think neither of those solutions are good for systems in dynamic environment, and a new approach is needed. Let's investigate the issue more. Consider that there is an online shopping system that we want to serve, that it wants to serve people around the country. Fairness of this system is about acting fairly toward all shoppers or equally, but what about other fairness requirements? What are their characteristics? Here, the initial requirement is about equal access for all shoppers, but let's consider that we found out that all shoppers are struggling for shopping. So a new requirement emerged, which is about giving those old shoppers higher priority, which is obviously a discrimination against other groups. So it is safe to say that fairness requirements are subjective, which means that they depend on the context and stakeholder viewpoint. We also think that these requirements are variable and change because of the changes in resources. For example, after a period of time, we decide to restrict number of items per shopping trip to keep the stock for a longer time. Also, we think that these requirements are uncertain at any point in time. They get more clear when time passes. For example, after implementing those previously mentioned restrictions, we understand that we need to exclude health-related items from the previous restriction. As you may have noticed by now, that there were some influences and conflicts between these requirements. The requirements about giving old shoppers priorities in conflict with equal access, and it is in conflict with requirements about selling health-related items at any time without any restriction. And what is the cause, or what are the causes? We think that different stakeholders with different and conflicting goals will specify different and sometimes conflicting requirements. And these requirements are working on shared resources. Actually, these fairness requirements are working on shared resources. This commonality can cause conflicts or sometimes influences as well. So we suggest adaptive fairness approach as means to overcome the mentioned challenges and satisfy fairness requirements and maintain such satisfaction. We think that adaptive fairness needs to understand and consider relationship between resources, fairness requirements, and stakeholders' viewpoint. Actually, adaptive fairness has three models in its core. The first is fairness requirements model that represent high-level fairness requirements and their decomposition. The second one is a resource model that represents different resources and their relationship. And finally, operationalization model is the chain that holds these two models together. These three models are the knowledge of the adaptive fairness, and in the paper we presented how these three are coupled together. Also, we used Maid-K loop as a feedback loop to demonstrate how adaptive fairness works in action. And finally, in the paper, we categorized and then discussed the derived challenges and open problems in three categories. First, capturing fairness requirements. Then we tried to see what are the challenges in or impacts of their satisfaction on other aspects of the system, and then what are the challenges of satisfying such requirements. Here, I only discussed the last one. For example, because of the importance of the fairness requirements for stakeholders and the fact that their satisfaction affect stakeholders directly, and because we are just promoting an automation or an adaptation of their satisfaction, verifiability and validity of these requirements are important. Also, for example, if you choose not to serve a certain group, you need to explain that to those groups or stakeholders. It meant that explainability of the system's behavior and these requirements, based on these requirements, are necessary. So thank you so much. And if you like the idea, just check the paper.
Thanks, Ali. That was great. So let's start the discussion. So I would go for from the order. Bradley. Bradley has a question for Michael. Do you want to ask?
Yeah, hi, Michael. Nice work. I really like the idea of perturbing the images to get different, error cases. But I'm wondering how you ensure that the perturbations are actually real. Like in the example you had of the heavy rain, you still had a blue sky, and the lighting was kind of still the same. But usually, when it's heavily raining, the light is much dimmer and the sky is gray.
Yes. So our technique does assume there could be a reality gap. So it is. I mean, the simulation environment isn't built into NWIL. NWIL relies on a simulator environment to be provided to it. So this technique requires, your simulator environment to be somewhat accurate. So we're leaving that up to the user to decide what is appropriate for their specific task. In this case, we are using ray tracing for the raindrops. So it should include information from the image. So if it's dark, the raindrop will be dark as well. But again, this study isn't also just focused on raindrops. We're just using it as an example. So ultimately, it's up to the simulator to decide, or the designer of the simulator to decide what is good enough for their specific task.
Okay, thanks. Yeah, it would be interesting to know whether there's some acceptable gap that you could have. I guess that's specific to the domain.
Yes.
Perhaps. It's still interesting to look at. Thanks.
Thanks, Bradley. So Danny also has a question for Mike. Do you want to go ahead? We cannot hear you, Danny. You're
Always the same issue. Michael, also from my side, thank you. Very nice work. I was just wondering here a bit. To me, it appears more like a machine learning paper. So it was not fully clear to me what actually, if you consider here something as a system and a controller that adapts that system, what could be here the system and what would be the controller? So later, when I saw you talk, maybe it is the meta learning that is the type of controller and the learner is the system. Is that the right observation, or do you see it differently?
Yes. So, this work is very much focused on just providing a mechanism for self-assessment of a learning-enabled component at runtime. So this, we consider this an enabling technology for a MAPE control loop. So you can like a MAPE control loop using a behavior oracle during maybe the monitor and the analyze step to determine if the learning-enabled component of a system can be trusted, or if you need to adapt based on the perceived context in the inferred behavior category. So this is very much just a meta-level self-assessment tool to be used by a self-adaptive controller.
Yeah, I can definitely understand that. Thank you for the clarification.
No problem.
Thanks, Danny. And I have to mention, if you have questions related to the most recent discussion, please raise your hand and you can ask. So Elias, do you want to also ask a question from Mike?
Yeah, sure. Thanks. It's a short question. Actually, if I understood correctly, you base your decisions on the meta classifier on the recall, right? Did you investigate precision F1 scores, other measures of classification accuracy?
Yes. So again, we're just demonstrating an object detector for this example of this study. This approach can be applied to other learning-enabled components as well. So we focused on recall here because, basically with object detection, you have different metrics like precision, recall, F1 scores. And we just focus on recall because it's simple and it captures like basically a nice simple metric for determining whether or not, or how accurate you are at detecting true obstacles in the environment. But this approach does, it's up to the user to define the behavior categories. So if you did want to consider precision and recall, it's just a matter of redefining your behavior categories to look at those metrics as well.
And does it have to do with maybe safety implications, that it's better to misclassify, to think that something is a car instead of missing some cars?
Yeah, our assumption here is just that, yeah, we're more concerned with not hitting a car versus being like overcautious, and like, because if we're just looking at precision, that would just save us from detecting non-real cars. But again, in a real application, you might want to consider precision as well, and this work can be extended to use that. We just didn't focus on that in the study.
Thanks.
Thanks for the discussion. Khalid, you have also a question for Mike.
Thanks, Michael. I suppose mine is tied very much to Bradley's in a way. So if I can phrase it slightly different to the way I've written it, but given that this is an open world problem, and that we have almost an infinite number of ways in which the system is going to change, how realistic is it to say, by adding some effect into the system, I can predict what's going to happen out there?
So yes, I mean, this is obviously a very challenging problem. So we kind of had to break it down to like simple cases and take baby steps. And here we're just assuming that, I mean, we can't handle unknown unknowns. We're assuming that we're just going to focus on known unknown phenomena. And I mean, in our view, it's better to have this behavior oracle in place than to not have any kind of self-assessment. Because even if we can't capture all raindrops, if we can at least capture a subset of raindrops, that's better than nothing. So that's kind of been our motivating factor here. We're not trying to solve all problems, but if we can have a simulator that can at least, I mean, again, it's up to your simulator and the known unknowns you can simulate. So if you have a very rich simulation environment that can simulate lots of different effects, then this approach can conceivably at least provide you some automatic assessment and prediction capabilities for those known unknowns.
May I just ask you a question that follows on from that? So in your opinion, is it better to have a simple simulator that you know is wrong, or a very complex simulator that you think might be correct?
I mean, again, that's very tricky. I'm not sure if I have a good answer for that, because I mean, obviously, the more complex your simulator goes, is the more assumptions you're making. And I mean, you could overfit to your simulations. So it is very tricky. And I mean, I don't know if I have an answer, and that's sort of outside the scope of this study. We're just assuming, I mean, we do make the assumption that the reality gap is sufficiently small and your simulator is sufficient for the task. If obviously, if the simulator is not sufficient for the task, then this approach will not work.
Yeah. Okay, thank you. Maybe an unfair question.
Thanks for the discussion. I have to mention also, I had a similar question than Jeff, but Jeff, do you want to ask yourself?
Yes, thanks, Michael. I thought it was very interesting. I have two kind of questions. One is, I have no idea of the sort of world of the vision research. And what I wondered is whether this approach has been used or is in any kind of discussion in vision approach. And then the second question is really, given the notion of these behavior predictors, is this a general notion that you think could be used in other circumstances? I would be interested to hear if there are other applications, other ways in which we could use something like this to try to minimize the uncertainty in our adaptive systems, other than vision.
So yeah, again, we've tried to design this approach to be generalizable to other sensors as well. Obviously, vision's easy to demonstrate. So you could apply this technique to other domains like audio signals or so forth, but you would have to basically change in our behavior oracle the interference isolation and the feature extraction subnetworks to apply to audio signals rather than image data. As far as comparing it to related work in vision related tasks or applications, I mean, there is a lot of work in generative adversarial networks that's similar, where I mean, I don't want to go into too much of a sideline discussion here, but with GANs, there's a lot of research in generating adversarial inputs and discerning different outcomes. What differentiates our work for those is that we are harnessing a simulator that gives the user more control over what type of contexts are generated. So yeah, that's my brief answer to your question, I guess.
Thanks, Michael. Thanks. I should give others a chance.
Yeah, also your work, I have to mention that it's quite close to the other paper presented by Max. And when we have a discussion with Max also, I would like to ask my question. But the kind of architecture you showed resembles the architecture you see in convolutional nets, right? So I was not sure like how you want to contrast it with, you know, as Jeff mentioned, the work that has been done in ConfNet type of work, and also in, for example, the direction of adversarial ML, because the whole community is working on this reliability aspect of the prediction. So that would be good to discuss it maybe also with Max, how you contrast it with this type of work. But I would proceed with the next question by Danny. Also has another question for Mike.
Sorry, I already handled that before. You can skip it. Yeah.
Cool. Colin has a question for Anna.
Hi, Anna. Thank you. It's very interesting stuff. I'm always interested when people talk about uncertainty. And I just wondered if you could give a little bit more detail of the types of uncertainty that you were considering here, or is this something that's going to work for everything we ever think of?
No, actually, I'm focusing on some specific uncertainties that I can elaborate more. So I'm writing in more extent in my paper about this, and also in the presentation, the longer presentation, I have explained it there more in depth on a running example on the use case that we implemented. So we have a robotics system that actually, although it's a simulated system, it has those, the realistic uncertainties are still simulated in the sensors and the environment of the implementation. However, at the beginning of my talk on the first slide, this was the only classification that I put, that I'm distinguishing between internal uncertainties and external uncertainties, internal originating from the systems themselves and external originating from the environment or the context where they're operating. I didn't go in depth. Concretely here, I have been following since the beginning of my PhD the work from Ramirez, Jensen, and Cheng on the taxonomy of uncertainty for dynamically adaptive systems, which really helped me navigate very well in my work. So concretely, we are focusing there in their work. Just for a bit of context for you, they classify 3 different levels of requirements uncertainties, design time uncertainties, and runtime uncertainties. I think self-adaptive systems should deal with runtime uncertainties primarily, because all the others could be anticipated in some way during the design of the systems, whereas the runtime uncertainties, for example, different sensor uncertainties or how the environment behaves, simply there is maybe no way or no best way to anticipate them. And concretely, we are focusing in this work on sensor failure and sensor inconsistency. I have my paper open here, so I can read to you how they define in their work.
I promise I will read it afterwards.
From internal uncertainties, from sensor uncertainties, as well as unpredictable sensor environment. Our use case is from a robotics domain. The systems need to discover and obtain tasks. So the unpredictability from the environment is where and how the tasks appear, because they appear with frequencies and patterns in the location patterns that cannot be anticipated during the design in order, for example, the model of the context in the knowledge of the system, of the adaptation logic in particular, to be created. And also interesting from this paper, because this paper doesn't focus on cyber physical systems, but on systems in general. There's one more dimension that we kind of identified, is the partiality of the observations of the sensors, because this is kind of really specific for the cyber physical systems, because only cyber physical systems have set. I think that's correct, yeah. Right, so those are kind of 2-3 classifications. What I meant in my first slide when I said internal and external uncertainties, they're very particular about what kind of uncertainties are we dealing with.
Thank you very much.
Thanks, Anna. So Yehia also has a question about an extension of MEDCAE. Do you want to ask yourself?
I think he has an issue with his mic, so he asked if you can.
Okay, so I remember the question. The question was how the systems can be distributed and have only one MEDCAE loop, if I'm not mistaken.
So it's about whether each agent has its own instantiation of MapK or not.
Right. So I had a slide on this where I explained that in my system, in our system, the MapK control feedback loop is structured accordingly to the master-slave pattern. So this is something that Federico talked extensively yesterday during his presentation on the mapping study. So we have multiple cyber-physical systems, and all of them comprise all separately, independently, with the monitoring and the execution component. So they have ability on a local level to execute those phases of the MapK, whereas the analysis, the knowledge, and the planning is centralized and in a way shared among all of them. This is my answer. I had a slide on this. I hope this answers better now.
Thanks for your answer. Maybe you want to ask your question for Max, since you're not here. Anna?
Yes, sorry.
Do you want to ask your question?
Yes. I'm sorry. I'm sorry. Yes. So thanks, Max. I looked at the presentation, the long presentation that you recorded yesterday, and this is where I wrote the question. I was not really focused after my talk now, and probably I might have missed it in both of the cases. But where are the AI black box components that you were talking? Because from the long presentation, and I skimmed through the paper, I just couldn't find it out. So are they part of the knowledge? Because you just kind of showed the MapK, you didn't show the managed elements. So are they part of the knowledge in the MapK, or are they managed elements? So are those the units that get adapted? If you understand my question.
Yeah. I think I got the question. They are part of the managed system. So the idea is here that we have AI-enabled systems, and where they incorporate these AI components that we view as black boxes, and they might produce incorrect predictions, and these incorrect predictions might propagate to the rest of the system, and this might induce severe reliability issues, and that is supposed to be managed by the self-adaptive system.
Okay, got it. I think your figure kind of confused me because this was omitted from your figure.
Okay, well, I take that into account for the next time, but thank you.
Thank you.
Thanks. So the next one, Radu asked a very interesting question that I also had about how you are going to use this reliability prediction at runtime, but I would leave it to Radu to.
No, that is indeed the question. So I like the work very much, Max. I was wondering how you plan to exploit the reliability predictions in a runtime context. Can you give us some details?
Yeah, sure. So first, the intention of the reliability prediction is actually to determine how good an adaptation strategy is supposed to or can manage an AI-enabled system. But I mean, the results might also be used at runtime in order to have some intuition about how the reliability would change. But I mean, also a result of the design time analysis is the sensitivity model, which is also very valuable and that can be exploited at runtime. So yeah, that would be my answer.
Yeah, but to add to this, do you have some concrete idea how you want to actually change the system under test? Do you have some direction that you're following?
Not specifically. I mean, there are a lot of design decisions that one might take into account. So maybe it's just switching the AI component with a traditional algorithm or with a more robust AI model, but it might be also stuff like inserting additional filtering components in order to pre-process image data, as an example. But this is actually depends on the use case.
Yeah, one quick thoughts that I had about with respect to your work and also relevant to Mike, specifically about this exploiting this reliability prediction. One direction that I'm quite familiar with is basically adversarial training or data augmentation, where you typically want to introduce new input to the model. So once you retrain on this new input, it will fix this unreliable prediction where you have Oracle. So basically, where you have the label for this new example, or even if you don't have a label, if you want to retrain it in an unsupervised way, it typically improves the reliability of the model, but we can have discussion about that later on. But
okay,
interesting work. I like it.
Thank you.
So next one, Danny has a question for Ali.
Yeah, Ali, I appreciate your effort for this ethical aspect in self-adaptation. It was a topic of last year, it seems, and it's nice to see work that follows up here. Now you said you will treat fairness in terms of requirements, which is a choice, an important choice. You might also consider fairness in other ways. You might say we design from the ground, taking fairness into account. It's not a requirement. It's something that you start from, like we do, for instance, nowadays with privacy. Yeah? Or you might say, I put it as constraints, not something that can be negotiated with other business requirements. So I wonder if you take a model for fairness requirements, how do you deal then with trade-offs? Because they're not only trade-offs among the fairness requirements, but also with the other business requirements. Yeah? If I say I give preference to older people, they might be slower and buy less and you name it. So maybe how do you deal with that here?
Okay, that's an interesting question. But I before just Bashar answered it kind of completely there. But before getting there, I will want to add one more thing, which is you're correct that you can start building the system having fairness in mind, but we advocate that that's not a good way to do that, because then you will understand that you missed something and you need to just come up with a solution for that again, or someone will, or the situation may change, as I said, and that's why we said it is subjective and it is variable and it is uncertain. So you need to catch up later with the problem. So that's why we said, okay, let's look at it as a requirement. And the reason that we went down to the past about negotiation is because most of the time, for example, there are lots of literature on counter negotiation or negotiation between fairness and or these kind of attributes, because you cannot satisfy fairness if you just see, if you consider it's a characteristics that any stakeholder may need at some point in time, or a share of it. So that's why a negotiation is there. And in terms of the thing that you said about they may interact with other requirements, business requirements as well. Yeah, that's correct. And that's why we chose to go with goal modeling technique, to consider that part of the problem, to see, we said, we know exactly that they will have negotiation or problems or conflicts, as I said, with each other, fairness requirements, but there may be conflicts or influences on other requirements. So for solving that, because we know that other requirements are working on resources which fairness requirements are considering or touching. So there is a connection between those requirements, fairness requirements and business requirements, because of the shared idea of resources down there that all of them are touching or monitoring or working with. I'm not sure if I completely answered or just kind of answered. But,
yeah, I see here also now a response of Bashar. Yeah, I see you guys think about conflict resolution, prioritization, and these kind of techniques. Yeah, okay, thank you, clarification, thanks.
Thanks. Next one is Mirko for Ali.
Yeah, I think this follows a bit what Danny asked, and it's related to this concept of fairness. I mean, how are you gonna measure fairness? And this is related to Danny's question, because if you want to trade off requirements, you need to have a measure of it, right?
Yeah.
And in addition, the same measure of fairness can be biased in the sense that different measure of fairness can show a different facet of the system, right? So do you consider this in your paper? Because sorry, but I didn't type to check it.
No, it's okay. Actually, it gets back to the point that I said, fairness requirements or fairness is a subjective matter there, and that's actually we ran away from that your question because we understood that it is impossible actually to know what is fair because it depends on the context. You cannot predict it beforehand. It depends on the context. It depends on the preferences of the stakeholders and other aspects. So we said, let's see what stakeholders want in form of fairness, and we built kind of a platform for them to describe what do they mean by fairness and as a fairness requirements. And then when you know what is fairness requirements or a requirement, actually software requirement, then you can measure it easier because you know what it is. For example, in the paper, we just shrink it, abstract it to a rule and action. Say, we said, okay, just consider when you decompose it, it's going to be a rule. If that's happened, then an action, something should happen. So that's how we ran away from that problem of just not knowing what is fair and how to measure that notion, which is kind of vague at start.
Thanks. So Janina has a question for Max. Do you want to ask?
Right. Thank you. Nice presentation, Max. Actually, I have quite a lot of questions for you, but I'll try to have just two. Let me go back there again to the question. Oh gosh, so many. Okay, I'll just stick to the one that was probably the last one. Was most related to this structural uncertainty. As I was wondering, the input data that you use for your design model and the data that you use for runtime model, how to make sure that they match each other in the sense like you need the information, the input information for you to run the model, right? And then you do some runtime analysis from what I noticed here in the paper. But I don't see how, for example, you like the operational environment that you use for design time data, it matches the runtime data because there may be a diversion, if I get it right. So then you may have like different component, let's say, importance from each other, and then you may have a mismatch. So how do you get the right, if I can say this way, the right data for you provide the analysis of design time, so you can say which AI component is really stands out here, and it will really match your runtime, let's say, operational environment. And the other one you may have answered, I'm not sure, but relates to the feedback loop. How do you tune in the feedback loop with your approach?
Okay, I would start with the latter question because this is fastly answered. And well, the thing is that we are actually currently not considered strategies that are control theory based or oriented. So the strategies that we considered are, I mean, the approach is also not limited to that kind of strategies, but we're more focusing on strategies that kind of works proactively because you want to, well, you want to circumvent situations in which false predictions might occur. And therefore our approach is more related to proactive adaptation strategies. And your first question, it's quite hard to answer, but I mean, the approach is actually based on an environment model, and the environment model just probabilistically models how the how specific variables of the environment evolve over time. So this is a dynamic Bayesian network, And these variables are connected to the properties where we want to augment the monitor phase with. And well, this timely evolution is either estimated by a domain expert, or it is in the best case you have runtime data from a comparable system, and you can estimate the model. But I mean, it's very hard at design time to make sure that that the models behave exactly like you would observe it at runtime. But I mean, the good thing is that if you want to compare design decisions, then it is oftentimes not that. So it's not that important whether this deviation of the design time predictions and the runtime, or how you would observe it at runtime, if the deviation is a little bit high, as long as you are able to determine at design time whether design decision A outperforms B. So you know what I mean. So you are capable of evaluating specific decisions of the strategy, and you can do this before the system is implemented. So otherwise you would realize it at runtime, and then you have to re-implement the stuff, and this might become very, very expensive. So I'm not sure whether I could answer your question, but I hope.
Yeah, maybe some of the work in the previous section, like digital twins, could fit in here. I don't know, but I think it's a nice problem that is open here for your research. Nice, thank you.
Thanks for the discussion. We are almost there. We only have one question left. Jeff, do you want to quickly ask from Ali, and then we close the session?
Yes, it was just a sort of, again, a general question, which is your approach and is what you're advocating peculiar to fairness? I mean, isn't this all part of the same problem that we're trying to solve in terms of performing requirements at runtime? I mean, the notion is that you've got an evolving system, you've got circumstances which are changing, you're trying to adapt to those. And so what you want to do is to be able to put various, let's say, requirements and stakeholders' desires against each other and come up with some way of dealing with this. Is this the answer for all of those, or is this just for fairness? And what can you tell me?
Okay, actually, it's not answer for all of those, and we can just abstract any problem in this field to a just problem of software requirements, elicitation, and then implementation, and all the problem. But the key point about fairness requirements, as Bashar mentioned in the comments, we actually, I'm not sure why we eliminated that sentence, but the anchor points of the fairness, describing fairness requirements are about, in our point of view, are resources. So whenever you want to talk about fairness, you are talking about resources, and resources can be an item on a shelf, or a CPU time, or any, or even a version of the stakeholder, a user, or a request of a user, or how you are going to treat. So that's the most important point of the fairness requirements, and that's make it interesting. But we said that they are uncertain, they are variable because they are related to resources, and they are subjective to the context, and that makes them challenging to elicit and then satisfy and maintain that satisfaction. But again, all of that argument is going back to the point, which is fairness requirements are about resources, and that's important. And I want to mention one thing, which is sometimes I saw that Danny said that you need some ground for fairness, but sometimes you cannot have a ground for fairness. You can say this is fair, and I can just say it is not. And we saw it, for example, you can say in this scenario, I want the best applicant, and the algorithm is going to just act discriminating against the group. And then you say, no, this is not fair. But from a standpoint of the owner of the company, it is fair because he wants the best applicant. But from standpoint of the society, it is not fair. So sometimes it is impossible to have a ground. So those are the points that makes fairness requirements interesting. And then those are going to drive the solution that you will give for maintaining their satisfaction and even their satisfaction, because resources is there, the trade-off, as there are a discussion, there is there. So that's the key argument there.
Thanks a lot for the discussion. Thank you all for participating to the discussion. Nice talking to you. Let's end the session. See you soon in another sessions.
Okay, thank you, Boyan. Thank you, everyone. I just want to remind everyone about the survey, the SIEMS steering committee survey, that you'd like you to answer, to go through the survey, please, for us to plan the future of SIEMS is important for us. So that's all for today. All right, I'll see you tomorrow for the last day. So far, so good. All right. Thank you for all the session chairs. Thank you for the authors. Thank you for the questions. Thank you, everyone. All right, I'll talk to you tomorrow. All right. Okay. Bye-bye, everyone.
Bye-bye.